Okay, that's good. And the third efficiency method is the CSF for stabilization method. And this one is, what can I say? I don't know, maybe they mentioned, let's say, some errors of the Bach method and can be used together with that one. And the core oscillation method deal with the second and third harmonic cavities that I have discussed a little bit ago. And I didn't believe it, how it works, but it really good responses. And efficiency or core stabilization method, CSM, efficiency can be made up to 9%. Branching length in core long, CSM is short. It's very, very advantageous because you can make the 2 or 3 meters Klytron instead of 1.5 Klytron, 1.5 meter Klytron. It's shorter. And the harmonic cavities, of course, the fundamental cavities that the main frequency everywhere, every buncher. But the CSM method is second order harmonic. It means a small cavity. And you can gain from the some money proper too. It should be make a high efficiency, then you have to use the oxygen couple. Not must, but it's better. Okay. This method is especially for L and UHF pump, suitable for low permeance electron. I'm not talking about the permeance because Kashik is also talking about a little bit, and it's related with the electrons, and we will see maybe magnetically confined electrons can be twisted. You have to be aware of their emittance and the twist parameters. Yeah.
Which method require low elements?
This one is the CSM.
CSM.
Yeah. Okay. So that's a very short. And this is the efficiency to the torches and method we are going on. That's the one also example for one design with CSM. And it's you can find it from the particle cell simulation, second and harmonic cavity collectors. Let's see. I'm not sure about this one. That's This is the frequency of cavities. Which one is 1293? Approximately 3 gigahertz. This one. This is 1.9. 1.9 gigahertz. Is the half of it about 80s? No, but this one is the half of this one, approximately the half of this one. This is the second harmonic of this frequency. Maybe the third harmonic of that one, I don't know. It's all those things small. And let's see if any dimensions in here. Diameter. So in meters, it's 25 centimeters. It's 14 centimeters. And then the others between this. So harmonic cavities, So it's the second harmonic is the third harmonic, and the smaller one. So what? Maybe all those cavity length is, if you add these meters, 1.3, yeah, it's more than 4 meters actually. Hey, yeah. What's the T in watts? It's 7.5 watts for input cavity. Beam voltage is about 54 kilowatt. It seems to that we have designed before. It's similar. Okay, we are going there. Is there an output power? Anybody sees the output power in here? No. Yeah. Efficiency is about 86. Yeah, 86. And that's the selectedness of not the selectedness. No, the 1.3 gigahertz is very important for us. We have discussed about 7 years before or later. And due to that, I have designed in COVID times some Klytrons. I haven't remembered the number of cavities, but some of this the explanations about the Turkish, because I have sent this picture to my friends or to some people somewhere, and these are the 2.7 meters Klytrons with a efficiency about 73, the biggest one, and others. Which one is the biggest? And these are 73, 16 ampere current of the cathode, 25 input, and output is about 2 megawatts. That's the basic design. It's continuous very Klytron. But it's not possible because you have to cool down about the 30%, approximately 30% of the power. It means output, yeah, it's about 600 watts power should be taken out by cooling. And it's not an easy one. And the less than this one is the CSM used in here. It's the smaller with respect to that one.
With higher frequency, 75%.
75%. Where? Here. Yeah. Okay.
This is all of them calculation from the simulation results.
Yeah, simulation results.
How to rate in real application?
Because can be done, but not realized.
Yes. Before all the machines, what is the rate of the realization application?
In CERN, not in CERN, maybe in KT in Japan, they are designing about 20 megawatts Klytron, but they are multiple. But using their all those efficiency as all those three of them.
Actually, it depends upon how good your machining is, how good your material is.
Yeah.
So efficiently you couple RF power or efficiently get out of
Stability to electron
efficiency of electron.
and metals, many things exist, but everything is possible. I'm not sure, but it's easier than magnet. I agree with me. Okay. Sometimes I go, okay. There's the multi-beam Klytrons. As far as know about the Klytrons, parallel beam Klytrons, parallel Klytrons. Let's see, maybe one. This one. You see, these are all of them are coupled. You have many Klytrons to make a single Klystron. They are collected into one, but they have different cathodes, but they have one input buncher and other bunches too, and one output buncher. Our thing is safe. You have seen it.
And
You see. Let's go back. Oops, no. This is the simulation result of the multi-beam Klytrons. But of course, with efficiency, it's about 22%.
82.
Not 22, 82.
82%.
82%, yeah. This is shown, requested by FCC. And it will use a future hardcore collider. I'm not sure the future circle collider will be conservative or not. Yeah. Everything is money. Okay. And this is the whole design. And the magnetic poles is also included in here. And this is collector. We are talking also collector because we have skipped in Tuesday. What's it and how they design it. And all those things in here. All those bunchers. How many bunches is about 8 and others. This is the input cavity. The outer point here is a input buncher. All of them has single exciting input here. Turn around this one. And the input coupler cross section. Single one. And this is the output coupler. Due to the high power, they made 2 output coupling, and they will together couple together later. And one of the which one is I haven't remembered it. They are designing not KG. It's designing more than 100 megawatt Klytron, multi-beam Klytron. Of course, it's a big power because they need the big power. I'm not sure if it's realized or not, but you can do. They can.
Using multi-beam?
Yes, multi-beam. Because it's not easy to make a single beam over 5 megawatts. It's long, and the mechanical problems exist, mostly due to the heat. Another one, I don't know how to use it, and very I don't know, sheet beam Klytron. The main problem in here is the cathode. you make a sheet beam electrode cathode, and other things are the same. That's a solid model, but it will be machined easily. These are the punchers. Now to clarity. Yeah, that's the cut. But how can you do it? I don't know. Maybe you have stick. Yeah, push faster or whatever. Push faster. It's not the good cathode. Good cathode material. I'm not sure. And for that, as a reference, you can read this paper too. It's 10 megawatts at 5 Hz repetition rate, 1.6 meters is very short, and 1.3 gigahertz. It's the short name is SPK. And I typed here's all the pictures from this one. This URL, and you can maybe want to read. Yeah, that's the collector that we have skipped for. These are the Klytrons from Philips, about 1.3 or 1.5 gigahertz. We have Tiro part, and that was the here is the output cavity, and this is the same. This is the collector. And which one? This one is copper, the inner one. This part collect the ions and the cool down or and to trap it in there. It's the waste basket. Waste basket for electrons. Its surface corrugated. You can see lines in here to increase the surface for cool down. And after there's a water jacket. And this is the cooling water input and the cooling water output the other side. Then it's a simple and non-active passive cooling. But one more pixel-related one that we have applied for proton is approximately the same thing. If you put a ring with a potential comparable to the output coupler, electron will slow down. Then you enter the collector. When it's cross and pass the collector, pass this field, then it's trapped inside. Because cannot and lose some of energies after striking the wall of the collector. Then it doesn't come back to the Klystron. If you come back to the Klystron, the resonance will be down, and you can lose the beam and the other effects. And then you have to trap it very well. This is some mechanical design, and all you are is there then other scientists or other engineers in from machine shop something. No, all you are physicists and the electronics. Then you need engineer to make heat transfer calculations
Chemical
to make machinery,
especially in chemical engine.
mechanical engine.
So my question is that, what will, let's talk about your design. What will be the energy of electrons when they are collected?
Starting with the atomic of the electron beams, less than this one.
Last one.
The last one is about the health of the first one.
Okay.
But we can calculate because it's it depends on the catcher cut.
Do we need
How to convert the currents into power.
do we need some X-ray shielding in this collector,
Sometimes, yes.
depending upon the energy?
Yeah, right. And you can see here, actually, all over this one, all the cavity has covered with about 2 millimeters.
Right.
Yes. But if you apply about 6 kilo, then, according to me, there's no exchange. Even about the 30 or the 40 kilowatts, nothing else. It's also so soft, very soft X-ray, and it can be stopped by the emitter. There's another use. That's still the complete. These are the complete collectors. It's an input for the cooling water, and others are the outputs. But I don't know the circuit in that. Maybe it's rolling around, or maybe there exists any circuit, cooling circuit. I don't know, because I don't hear the reactions. And this is the answer your question. And this is another output next to catcher cut. And these are the output antenna. It seems to be take some power out. If the voltage is higher than the anode voltage, then it should be lower. But in this case, is the generation of higher order noise. That's the home coupler. Higher orders mode couplers. And it's negatively affects the other resonances. And it will, all the things is, the other modes will be dumped in the cavity sometimes later, but it converts to the heat. Then it should be taken out from those cavity, and it will be has gone to the waste basket. And this is the fully filled with coal down and the extension of this one is the antenna. In other words, that's your answer for your question. You can you can take output anywhere. You combine later on. But the intensity is very low at the middle of the cavities. In only low the bunch of cavities. Due to that, you are increasing all the bunching into the last cavity. That's the question of the. Yes, answer was that interesting.
It's busy. He is busy now.
Yeah. Okay, that's the collector. But how do you know that? We are going to see. If you see the reflected back, some electrons reflected back, then you add such a coupling in here, cool down the system, cool down or to die the higher order mass. But if you have such a mode in your simulation, I suggest take down the voltage or higher down voltage or play with the cavity dimensions. That's my suggestion. Well, yeah. Clicking on the these are the Klytrons softwares. You know everyone. This is the HA disk. In my opinion, it is the starting point of to make a design or simulation for Klystron. This basic one, basic and a boot one. And other, my favorite is Klysi. All of the softwares. I only deal with the Klysi. That's the CERN software written. You can download it freely, 1 and 1.5 dimensional one. And 2-dimensional one is, it's secret or no, I don't know, maybe so I'm not aware of it. But you have to mail to some guys to show, to get the Klysi. Why do you use it? And you have to explain. I'm not sure. That's the 6 years before. I not checked the last days. And Klysi, I'm not sure. Maybe it's free or not. Klysi 2D. Magic. You see, it's possible. Of course. And this one is the first written one by Slack. I'm not sure, maybe the first one. And from Thales, if Thales exists around places, then you can't get without money. It's possible, you know. Why would you need to make some cavities or Klytrons or something, the tubes, microwave tubes, or magnetron? You can buy from Thales everything. Mostly it's forbidden. It's difficult to make a purchase. I have bought some tubes for make the main mount by RF2 accelerators. It doesn't respond to me more than 1 year. When I was in CERN with my friends, we asked the guys, RF guys there, and they write a single one, a 2-line notes, Thales. And less than 20 hours, they called it. They told him, they asked it every time. After they buy these tubes, in every 3 months, they write mails to me. They want to visit us. That we have reached. And after 2 years, we have to write some papers about the accelerators. Then all those things is finished. And last 10 years, you can get anything. For the next 10 years, you can get anything. Maybe Klytrons or magnet or something else. It is strategic. You know it very well.
Certain defense companies in Turkey, they cannot get even screws.
Yeah,
But TÜBİTAK is more neutral. You know, we have some defense programs, but at the same time, a lot of civil programs. For civil programs, it's relatively easier to get these components. But in general, these critical parts in the components are very difficult. You need to prove or end user. They want to make sure the end use is for civil purposes.
due to that, we need some vacuum electron devices, people. We need some society. I think you are the start of that one. Maybe you are the profession. You are going to be professional about vacuum devices. It's not, sometimes ago, everybody talks about the vacuum electronics. It's not electronics, not only electronics. It's also physics, a great part of that related with physics. And you have to make some associated with your friends from electronics because you need supply and you have to measure something. And mechanical engineer, maybe you need some metallurgical engineer related with the coppers or other metals. You have the material engineer. But the first three is physicist or physics engineer, what it means, I don't know. And electronics and mechanical engineer. And of course, you know, you should have many technicians. I had the chance like that, such a place, you know. Okay, and CS particle city, of course. That's when everybody likes it. COMSOL, those two are multi-physics. HFSS, where is HFSS? It's possible. Again, Thales, impossible. Magic 2. But if you make a simulation, you have to optimize it. Yes, C has also optimized. Extra optimization you can find. Most of these softwares also has optimizer too. These two is okay for you. Yeah.
Do we have free software showing such a device?
AJ disk and license. Red 2. This one and this one.
It's free.
It's free. You can download.
Yeah.
You can download it. Some version of Klytrons. It's enough to make a Electron. 1 dimension and 1.5 dimension is free, but you have to write an email to the person responsible for the software. He has also write this software, and you have to make the right ask for. Why do you use such a question? I'm not. And as a note at the right side, yeah, AJ disk, Magic CSD, you have to validate all of the design from here. But if you read the Class C 18-page manual, Class C has a validation for CSD. It should be reversed. But it's better than CSD. I show you, maybe later on. Yeah, maybe because we have made the benchmark between CSD and Klytrons. Sometimes I say Klytrons or Klytrons, whatever you can. Which one is better? I don't know, because we don't realize it for some reason. Okay, let's go. This is the AJ disk. What's this? This is okay. What's the AJ? American Java. I don't know what it comes from. American Java. And you the address is here. I put some extra there somewhere. Very good software. All of the errors that I have seen up to now is not greater than 2.5%. It's very good for engineers, extra good, but it's not good for system machine. Engineer has a tolerance of about 50%. In civil engineering, 50%, 100%, no problem. But in physics, it's 2.5 is enough for realization of question. It's bad. And you can find some extra Turkish manuals, because one of my friends, those from London, they I have mentioned before. Yeah, I have remembered their surname. There is no Epsign. APSBMOE. You can write her and you can take any answer you ask. It's many has been translated in Turkish. And you can find many things, resources and accelerator terms or anything from here for mostly in AJ disk. How it works? I don't know the AJ disks. I didn't work it because one of my young ladies, she was very well professional in this one, and that's the explanation. The AJ disk, how it works. You can read it, going deep side of the AJ, and you can find all of the formulas in here. But how can you realize the reality? And the algorithm of the flowchart of the AJ disk also. Yeah. And this one is not, it's also one dimension. What's the difference between CSD? CSD, 3 dimension. You do that one, you can define a mesh takes slice discs. Disc mean comes from putting make slices, one slice sold, next slice sold, and etc. The name is come from the disc or slices. That's the main feature of the AJ disk, and it's a very old software. But still working nicely. Yeah. And you have to couple with the cavity design superficie HFSS and 2 or 3 dimensions for peak. That's all.
Yeah. Does it use finite element method for meshing? I ask this due to HFSS, cavity design.
It's
So
a different.
HFSS
You have make it only cavity
Ah.
with the supervision or visual HFSS. Then you can transform it to the HU disk.
Okay.
I don't know how it works. On the slice. And you can slice with the number of slices or discs. You can choose it. And that's the page. This was also translated in Turkish by the writer. I'm not sure. You can find from the internet. Let's see what how they will solve it. I'm trying the first one. That is the first one to try to put those things into place. This is the Charge design for B factory. Janssen is the famous Klytrons or cavity. And you can write here voltage, voltage. Yeah. At first, potential, it means about 83 kilovolts. And then current, electron beam current. What's your main frequency? It's okay. What's that? Carrier frequency, you don't need the carrier frequency because you don't have carrier frequency too. Disk to radius. You put a radius, some tube, whatever you need. What's the rule for the fun? It depends on your design of the electron. What's the output of what's the dimension of the radius? Diameter, not radius. What's the diameter of the electron? Then you all know the relation 2/3A. Or vice versa. If you choose a tube, then you make an electron beam such a electron beam with desired length. It's okay. Beta. What's beta? We have told it's coupling coefficient. How do you write it? I don't know. Yes, you can write it. 1. It's okay. You have to try it. In class, some software, maybe in this tool, I'm not sure. Or if you press the start, it's automatically calculate and put their place. Classes do this, but I'm not I don't know the age in this. And how to. Oh, yeah, I'm sorry. It's similar to the Kleist. Then some of the less d millimeters. What is that? Gap length. You can write it. You must write it here. And frequency for each cavity. You can write it. Which one? It's okay. If you write these terms, it optimizes and calculate the RQ parameters that we have used in the cavity lecture automatically and cures external cure or the unloaded cure or loaded cure. It's automatically filled this position and here. I'm not sure, but you have to check it. Beta can be automatically inserted here. GN, of course, it depends on it. Depends your instrument. In our case, let's say 13 watt. It was. This K import Gaussian K superficie can be transferred to suppose, which I don't know the others. And it was written here. It's possible to make sweep of frequency. Maybe you can, let's say, 1.3 gigahertz. You sweep from 1.299 to 1.3333. Let's say you can sweep this frequency range. Okay, then you start the. It's okay now to start this button, then it will be do everything. I think so. You have to read the manual. If you, yeah.
Does the coupling coefficient depend on cavity dimension or
Gap length
gap length?
and the gap radius
Gap length.
mostly, and the voltage and the injected power.
Yeah, I have comments about this beta coefficient. It depends what sort of cavity you want. You want high cube cavity or your cavities.
But the high tube cavity is a beginning. It's okay. It was okay.
Then you set beta greater than 1. If you want critical
No.
coupling, it's less than 1.
Beta should be less than 1. It's 1 is the maximum.
And then it's when less than 1, it is undercoupled cavity.
Should be 1. Yeah.
It's critical coupled when
Yeah,
beta is 1.
coupled. And maybe I have skipped that one. If you make it beta is equal to 1, then you are injecting with the magnetic coupling. You remember the magnetic coupling, loop coupling. If it's underdamped or is overdamped, you have to turn a little bit right or left and follow it from the oscilloscope or instrument which are using. It deviates because the surface of the loop is not exact. It can't be done exact. And the current in the loop can be different. Due to that, to control the flux, magnetic flux. You have seen from the video, it's very well defined there. If you some left or right, the loop, the flux will be different, induced to the volts. Beta will be 1 in some positions. That's right, I think. Due to that, but it will be changing another stationary in that, because everything has changed. I suggest that the mechanical engineer, due to the because heat transfer is their own subject. It's important. Should be fixed about 1 degree, maybe less degree. I remember from the CERN is about less than 0.2 degree stability. In RFQ, that we have about 1 degree has moved the frequency about 50 kilohertz. Our frequency is 352.21. It goes to 3, it goes to 20 minutes, and if your cavity fixed, of course fixed, then the frequency is changed, everything is changed. That's not a great physics, it's engineering. Due to that, you have to make a collaboration with engineers. Generally, you need them. And electronics, of course, you need high current, high voltage, and of course the stability is the everything. Okay. Yeah, you can read it. That's the you have maybe you have right to Chinchikai or Igor. Both are right this software. Two dimensions is not free. Maybe you ask for the reason. But 1 and 1.5 is right there. So the bridge to get between the fast and that we can download it. It's very stable software. Yeah, and you can get everything. I'm going to discuss it later. And these are the content of manual. And you can find many output related with all bunchers, all fields anywhere, and the animations. Yeah. And also, I'm not sure about the AJ disk, but the Klytrons has also included the space charger thing. This is the Klytrons. The time or after break. Break, small time.
we go to the lunch at 12, I think.
12:50.
We go to and 12,
I think I need about half an hour or after that one.
lunch.
No, from here. And half hour.
Can continue then.
Okay, then go, I finish off.
No, we can continue then 12, 13,
Okay,
20. And then after we go to the lunch.
okay. And this is the class. The first page of class is in here. I take this one from the man. Let's see what we need to fill all of the spaces. We have to click this one to make a new project. Or open the old one. Save as if you know. You make electromagnetic simulation. Just not electromagnetic simulation. Or global simulation. Power range. Power ramp. How to increase how to gradient of the increasing of the power. You put it, but don't play with it. Image C should be -1. There's no minus there. No. It should be -10, you will read the reason of that. This is the beam voltage. That's the same for HADs. 20 kilowatts, let's say. And be sure about the units. Beam current, outer radius, this the beam to outer radius. Yeah. It means if you use hollow electron beam, it means you have the middle side is empty. If you have a beam, you can use anything anywhere. I don't know.
Does it beam annular beam?
Annular beam, yeah, that's the right name. Annular beam. You can then define the outer radius, inner radius. If you use a single beam, Gaussian beam, or whatever you design, it should be 0. Tube radius. Okay, I know the tube radius. 5 centimeters. And it should be what? 2/3. It's about 3 or around 3. Because if you don't struggle with the grid or griddless or gridded structures and the coupling, the smooth coupling, then you have to write times 2, 5, 10 over 3. 3.3 is maximum, is okay. But you can a little bit lower. Then it means it's 3. Then you need a 3 centimeter beam. It's okay. Beam number, you can multiply. Because every beam is the same. I'm not sure, but at the end they are multiplying all of them. I think so. And layer number, put 1. This is the frequency. In this example, it's about the 5 gigahertz. Reflection from output. But before that, we have to see reflected electrons, it's no or yes. What's that? I couldn't. Successful iteration. It should be yes, and the reflected electrons should be, must be no after simulation. If differs, then you have to go back to start again, changing something. This is the output section, simulation result. But go back to the same place again. Will efficiency optimize? Next slide maybe. And the accuracy setting, it depends on you again. Source change, field order, 8. It's very, very good. And division number in K. Don't use this one if you're dealing with more than 1 meter. Everything is fine. Values. This is the extension source. Okay. And if you make a simulate, after that one, you have fill in the blanks, you filled, then you should be here. This is the number. 1, 2, 3, 4 is in order, the number of cavities. Then the next one, type. You put the first one is a 0. It means it's an input cavity, the first puncture cavity is input. And the second one is a 1, third one, 2, and etc. The last one is a catcher cavity. It should be -1. And it's the frequency after the 3 method of high efficiency. It's not the same. Maybe we have of the multiplied by 2, 3, or harmonic frequencies exist, or maybe I maybe change a little bit. I give some example. And let's skip this one. What's that? Q0, Q in Z. Z, the drift line. What is that? It's in millimeter. It's okay for 5 gigahertz. Gap distance. You have to define for each cavity. Noise. This is the most important one that we have discussed. The rounded or sharp edges of the cavity. You make it sharp, then the field about the near the gap is very high, and it will destroy the field there. And it should be rounded a little bit. This is the nose. I'll give some examples too. And sigma. This is the one. This is LC in millimeters as the gap length. And the sigma, conductivity of the material. It's copper, it's about the 65 or 70 or 60 million should be here. If you are using copper, then you have the 55 and your 70 and extra 70. We have designed with an aluminum, then it's the 30 or the 35 and extra 60. I don't know if it's agree with the exponential one. I don't know, maybe not. All should be integer, and it's okay if you write the first line, and if you press the update cavity, R over Q, and other something, these ones will automatically fill. Because you know the dimensions of the cavity, you give the material, it's okay. That's the formula to be computed. And for you, it's ready. It's ready for you. And if you write the same thing in the second one and third one, etc. And if you simulate, oh, let's go further. No. That's one the. No. And you have the plot settings. How do you need some plot? Maybe you need some plots or some animations or anything. You have to choose it. And some efficiency enhanced optimizer. You can check some boxes, or you can write something there. I think I have such a place. Maybe we can do it later. And after you have to not starting with the simulation, you have to if you think some of the lines in here with mouse, if you click it, then update cavity, you will get about 5 graphs or 5 drawings related with your cavity and the fields. That's one of the, even by the Klytrons, if you update the cavity, after the update cavity, then you can see the fields in here. It's not bad. Okay, let's see. This is the gap. 3 centimeters. Nose. The nose radius of curvature is the 9 millimeter, and other things. Sigma is the conductivity. As RC. Okay. This was just done for this. This is the Phillips Electron. And this the field shows us such a pattern.
Sorry.
Yeah.
Maybe I lost it. You reverse engineer that dimensions from the Phillips and put in the Gleiss, or
Yes. Maybe not from, maybe the others, some place from exercise, I'm not sure. To see the field of this in the time of learning something. In members, young people, students. Of course, all those things were angled. Cavity with rounded noses, not sharp. And also, you can do it with Klytrons. Because Klytrons is extra model. It's to write around it, nozzles and everything to do. This is the 1.3 gigahertz. 1.2 gigahertz simulation, not the results, but the design. It's 5 cavity. It's 0 is the initial one. The input cavity. Its main frequency is, of course, 1.3. And after that, play it with the small differences. The last one is the same. Same frequency with the input. But we know it from the back. It should be a little bit way. That should first. That's fine. And this is IQ automatically computed by the device. This is ML, as you see. This is also automatically computed for the class. And this is also, this is the Z depends on you. Of course, this section is completely yours. You should put everything here. This is the 58 millions. This is the sigma. Or I'm not sure, maybe from maybe copper. A sigma and RC. This is the north. Some is rounded. Some is not round. It's crazy, I don't know. And north gap, you see, somewhere is 36, somewhere 40, somewhere 60. You can adjust all the things. Those all it means. Many iterations you have. It's impossible by hand, and it's for 5 or small bunch of cavities. It's not for single computer. You make it with computer file. But I'm not sure about this as the AI. Somebody's talking to me about it. It's not that it's a computing time. It's some computing time, processing time related to processing time. And on the 3 cavity in my computer, the old one, 10 years old, it takes about more than 5 hours. It's only 3. But if it goes to the 8 cavities number of cavities increase, all the things as low. And okay, what we do now, you can add cavity pressing this one. And behind of which one? You can delete some cavities in here and giving the number. And this is the most one. If you make, if you don't make an update, it's no problem. If you start with the simulate, first it will be updated by the device. You don't need you. Doesn't need you. But you should check this one to see the field map. Finally, it's an extra information. And these are related with the some of the noses parameters, maybe read it from the menus. Yeah, that's all. Anyone complicated? Hey, let's go further. Why do you put this one? Ah, yeah. This is another optimizer and plot settings. And these are the default values. You can't change it as a first try. After the learning of everything, you can change it. This is the minus slot using this. And the frequency and the other things. This is the plot setting. Number of trajectories that you want. And extension limits, Z cut it, etc. And your figure of you can on or off, you can give animation, you can get the text output, you can obtain everything from here. And the first two model is easy to read, and please understand I have discussed all the things up to here. This is the important one to my optimization and to my the real design. That's the relative nose, related to gap. You see, this is also in a model in device. You can make design, or you can enhance your design with this third section, classy electromagnetic model. All of them related with the gaps and the noses, land, and etc. Because all the sources of electromagnets of the signals characteristic is related to the cavity. Due to that, I want to be talking about the cavity state. You can make the good cavities, then good results from the Klytrons too. And most of them we have discussed all of them. Then you are going to make it well. And this is the most important one. Yeah, this is a picture. If you put these lines into places, all the cavities, if you click the update cavity for each line, you get 5 graphs before the simulation. All was related with the fields, stored energy, and other things. That's the field. That's the field stored energy. You can check before the simulation. If you start the simulation, then you have to wait about 10 hours. Due to that, you check all the cavities pressing this button. And you can be sure of all of the physical parameters. I had said before, in COVID times, I don't know this one. Always pressing the stimulate button and waiting 2 hours. And 2 hours, 2 hours, and the time goes on. It's very, very slowly. Yeah, it was a good time. Okay, that's suggestion. It depends on your style, talking style. One more page. Okay. After the completion of the simulation, at first we have to check for true boxes. It should be yes. It should be no. Must be. Should. If it's reverse, one of them. If it's no, go back to your design. It means mostly some of the cavities has a voltage and previous on voltage. Then you have to add a damper on coupler, mechanical design. But you are in the phase of design, you are in phase, your design phase, then change something or some of the, let's say, take it out as one of the cavity, or change the frequency, or play with the parameters, play with the physical parameters. And you will see P out can calculate it in here. It's about maybe taken from the 1.3 gigahertz design. 2 megawatts, efficiency 73 if you're using PACOM or CSM. And gain is 45. Electronics engineer. 45 is a good one. Yeah, 45 dB. Right? Yes, 45 dB. And it's a good design. And this is the graphical output. Of course, you can't see the definitions, but whatever you want, you can get it from price. And these are the animations. It's complete design package of software. But then you are downloading in the phase of installation, if your computer somehow the other programs, I don't know, the programs related to graphics and etc. It's about the 1 GB. You have to wait about maybe 1 hour. I'm not sure. Extra downloading should be done. In other words, Class is not a big software. Most of the graphical, I don't know, the graphical routines. You have to check all of them. And the design that we ask for. 352 megahertz, 0.21 is mostly used. All of the RFQs, 90% or more than this, with the same frequency. All over the world. This accelerator has been done in the former name is TAEC, Turkish Atomic Energy Authority. Now it's a TEMMAC. I'm not from TEMMAC now. It has been completed in 19, not 19, 2019, end of 2019, the operation was completed, and RFQ gives us the current the accelerated protons, and the Turkey will the fifth country making RFQ or first accelerator on it. And this is the 12th country, one of the 12th country in the world. And that's the designs. And we checked the design. We have used LIDOS RFQ design program. And one of them, there was two programs in the world. From Russia, LIDOS, and one from the United States. I've forgotten the name of it. I couldn't remember it. But it's the same price, $7,000. We prefer LIDOS, not prefer. They didn't sell us. I asked, why? They don't know. They didn't know. Everybody's told between it's close to the CIA. It's very common, but they didn't sold us. And then we prefer the LIDOS from Russian software. But another thing, the seller of the LIDOS, American, the same price. There's not one guy selling the software of Russian software. And we have done it. LIDOS gives us the true results. And after that, some guys are keen. Write something about that one. I'm not sure what it is going or what's the result. That's the story or some memory from about 2012. And there's the check for the okay, yeah. This is another problem. Plus 2. I've talked about the Thales. And I looked at the 2. I have talked about some RF guys from CERN. Instead of these 2, I want to make a Klytron. Because the accelerators needs to be very narrow bandwidth amplifiers. Klytron is narrow band and used in accelerators. And for that one, I have a time, 24 hours every day. We have jailed to our home, due to COVID, of course. And I designed that one in 3 months and checked after 3 months and etc. This was the drawings of engineering drawings of the this Klytron. Our deserve is about 85 kilowatts. But this, according to the Klytron, operates about 150. 54. And for cavity neon, you see some extra sections there. It's the cooling spaces, not Well, this was 1, 2, 3, and 4. What's the input? It's very low. All devices we have. 83 kilovolts, not 83. 33 kilovolts, in current 7 amperes. And outer radius, of course, 50 millimeters, tube radius. Very easy, huh? It's a big dimension, big sizes. It's very easy to make a machine because the frequencies they allow. The diameter of cavity about here. It's easy. But the price of the copper is very, very high. Due to that, we assume that we start with the aluminum and the resistivity multiplied. But the 150 kilowatts is taken from the aluminum. It's realized? No. Okay. The upper one is the CST simulation. Everything was tracked. It's the dispenser cutter. This one chosen selected code. It's about 7.7. Or here it should be about we choose it about 1000 degree to make it long life. And the other engine drawing something like pink. That's our installed space. Yeah, that one place. This is the Palace tetrode amplifier, main amplifier too. Its price about $40,000, 40,000 euros. And there exists here, some here. This tube is in the white color. It's a blue one. It's a 45,000 quality adjustment. It's a box, rectangular box, and a screw, or similar to screw. It's tuner. That's all. So all those things are about $90,000. And I've struggled 1.5 years. This is the left, or in old times. If you visit that one, no accelerator there. Empty. Okay, it's another history. That story. And this again, the higher output in here. And this was the accuracy second one here. Okay, yeah, let's see there. You see, PR 153.8 kilowatts. And the gain is 40 decibel. It's good or not, electrical engineer? It's 40 decibel is okay? Yeah, it's good, right? And other values. And is that one preamplifiers, oscillators and preamplifiers. The three cascaded amplifiers exist in through the tube. This was all done in Turkey, in Ankara, in local sources, one of my friends. Everything is Turkish. And this is the current 250 amps to feed the tube. And here is the accelerator. Yeah, it's the thermocollator. And we have make a benchmarking with the CST and Kleist. You see, Kleist approximately 154. CST has calculated 150. It's 2.5, approximately 2.5 error between us. Which one is the better? I don't know. It should be realized. Okay. And this is the radius related to frequency and other things. This is the Klytrons text that we have talked, that we have discussed up to now. The only thing that we have left out is the magnetic field, but it's easy for you. You have to put a solenoid onto around Klytrons, but you cannot run 2 meters because you can, but it's your total supply problem arises because the voltage of the resistance of the copper or the whichever it is will be high. Then you need some extra voltage and some extra current. Then your small segments you can do it, and it's not a problem. You can find any design for them. This is the some formula to help you a little bit. Engineering formula. Is it valuable or not? I don't know. Because Clarice doing everything. This is the only appendix one. You should be careful about how to pack, breakdown, and in the tube. And one point, gap length is often approximately equal to the inner radius of the brief tube. If you make a design, you should be in mind. Everything has the shortcuts. This is the best, one of the best shortcuts. And if you manufacture a Klytron, you have to do everything really as shown in here. But it's not a big deal. Don't be afraid. Then now, I have to ask you a question. Are you ready to design and construct a Klytron?
Yeah.
Oh, it's okay. And you? Yeah, you can do it.
Maybe.
Huh.
But I have to study.
This was not a good lecture because one of my ear was closed. I'm not this, but I have a problem. Okay, one more picture. Now, the same question. Are you ready?
Yep.
The left two pictures is okay. At the first, at the previous page. And the second one, it's empty space covered with some metal cavity and some pipes. If you make a good simulation, good design, and somewhere some people make a cutter and make a electron gun. That's it. Then you need a mechanical engineer and more technicians. Please tell what's the difficult place? You see, that's cylindrical chambers. Yeah. This is huge coil. And this is the cluster. This picture from Korea. But our friends, students, take this photo from Korea and send to me. You have to put it in the magnetic field. That's all. One of them from Thales, from British CPI, wire. It's the wire. If you think about the cavities, it's such a metal, tubes, everything is tubes in here. But we asked something about to make some adjustment of the cavity resonances. You have add small tuners mechanically. And the vacuum is important, most important. That's another subject. It's a huge subject. It's someone else's problem. Okay. It is bonus. And Mohammed talked about the coaxial magnetron, and I remembered one of the pictures that I've taken before. 7 or 8 years, 7 or 8 years before, you see, 2018. And this picture, the heater was broken, has been taken by Dr. Let's see, 7 years before. We have talked about the Klytrons, and all those years has passed out. What's left? Nothing. Right? Okay. And I'm thankful to the organizing committee, leading by our committee. So that thanks to my new friends from abroad, and lecturer, of course, and from Turkey, and I will be talking about now. One of the staff related to the others of room, infinitely serving tea and some snacks, tea, coffee. I'm thankful to them also. I'm thankful to you. You are the best generation will be doing this one. I hope you will be the best professionals in Turkey. I think so. Enjoy your life. You.
Okay. Thank you very much, Mr. Alaçakır. I believe and I think he is very good experience in this area, and I am lucky for that reason. We will be again. I hope together a chance fight to be. Thank you very much, and we will Is there any question for about this presentation from Zoom? Okay.
One question.
Yeah.
What was your input RFR in your design? This 352 Electron,
It's about the 30 watt.
13 watt.
Yeah, let's check it. Go back. Input power, yeah. Ah, yeah. No. Oh, yeah. Oh, yeah. Pay in, it's about 50.
Okay.
50 meters. Because we have a small device, about 100 watts, with the same frequency, to make expanded cavities before the construction of the accelerator. 15 watts. I have to change instead of the tubes and all of the preamplifiers and the supplies and the big transformer at the back of these units. Was a huge and very heavy instruments there. We change with this a small, such a small power supply or amplifier, and current supply, electron, and the Klytrons itself. It's okay. But another, it's a technology.
Anyone is working in solid state power amplifiers because I think to
Yeah,
200.
the preamplifier of the unit, the last one, before the tube, it's about 8 kilowatt. 8 units. It's about 6 kilowatt. 8 units will be combined together. Because ready to use power amplifier, power sources, you can find about the 200 to 500 megahertz. You can find. And if you combine all of them, it's about 700 watts. You combine all of them, then one of them, 2 megawatts in circle. More than 10,000 units was combined. Huge salon has been lost. But there exists advantage of it. If one of them goes out, then no price. It's only 500 or 700 watts, about 2 megawatts. The towers, more towers, you can find the pictures.
Thank you again for this great presentation, Mr. Alaçakır.